Today we're going to start talking about our first equation of the chapter, our specific heat. So to begin talking about that, we're going to kind of break down each of the variables in the equation. The first variable that we have, okay, so our equation, all right, is Q equals M cats, or mass specific heat, delta T, which is our change in temperature, and Q stands for our heat flow or our energy. So we're going to look, so again, Q energy, M mass, C specific heat, and delta T is going to be our change in temperature. So when we're talking about this equation, it's talking about heat flow. So where is energy being transferred? If it is a positive number, then energy is being absorbed by the system from surrounding. Okay, so remember, the system is what we're talking about specifically. Everything else is the surrounding. So if we look at this diagram here, the green solution is our system. Anything else minus that green solution is going to be our surroundings. So if it's a positive Q, then energy is transferring into the system. So the system is absorbing energy. If it's a negative Q, which we're seeing here, energy is being transferred or released into the surroundings. So the system is releasing into the surroundings, and that would be our negative. Okay, and so remember, here we have releasing energy, so this is talking about exothermic, and then absorbing energy is going to be an endothermic reaction. And again, you can kind of see the colors represent the transfer in heat, and you know from yesterday that we talked about endothermic tend to be cold to the touch because they're absorbing energy from the surroundings, where exothermic, they're releasing energy into the surroundings, which is what we're feeling, and so exothermic tend to be hot to the touch. So again, a hot pack would be an example of exothermic. Endothermic would be an ice pack. So we're talking about endothermic reactions. Again, it's all talking about the system to the surroundings. So endothermic, the heat is transferred from the surroundings into the system. So, for example, an icicle melting as heat is absorbed by the ice is an endothermic reaction. So again, the ice is absorbing heat, causing it to melt. So the particles themselves are absorbing heat, which is an endothermic. So again, endothermic, absorbing heat. Exothermic here, the system, which is the white box, is releasing heat to the surroundings, which is the surroundings is what is outside of the system. So here, burning a Bunsen burner, okay, it'd be hot to touch, so we know that it's releasing energy. So that would be exothermic, which would have a negative Q, and here we have a positive Q. So now we're going to talk specifically about what is specific heat. Okay, so specific heat is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So every substance is going to have a different specific heat. So again, it's the amount of heat that is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So for example, we're going to kind of talk about water. So it may take 20 minutes to heat water to 75 degrees Celsius. However, the same mass of aluminum would only take, for example, 5 minutes. And then the same amount of copper would only take 2 minutes to reach the same temperature. Okay, and this is all dealing with our specific heat. So why is it that water would take 20 minutes to heat it to 25 or 75 degrees Celsius? Aluminum would only be 5 minutes and copper would only take 2 minutes. So why is because they have different heat capacities, which is a good thing. We need water to have this specific heat that it has, otherwise we wouldn't be able to survive. So again, all these metals, and substances, they don't have to be water or metals. So water, aluminum, and copper, they all have different heat capacities. These are all the different values that we're going to use, and you'll get these on the test. Okay, we're going to talk about it in joules. Calories are probably a unit that you're more familiar with. If you think of like when you go to the store, you look at the calories on a box, it tells you how much calories are in a specific food that you eat. We're going to, however, use joules. So we're going to use these values to the right over here. So you'll see water has a very high specific heat. So it takes 4.18 joules of energy to raise 1 gram of water by 1 degree Celsius, where aluminum is a lot lower. So if we look here, it would take only 0.90 joules of energy to raise 1 gram of aluminum 1 degree Celsius, which is why we said it would only take 5 minutes. And then copper is even lower. That's 0.39. So it would only take 0.39 joules of energy to raise 1 gram 1 degree Celsius. So that's why that one only took 2 minutes. Okay, and you'll see they go down. Gold has a very low specific heat. So again, different substances have different capacities for storing energy. Metals have very low specific heat, which means that it doesn't take a whole lot of energy to raise 1 gram of a metal 1 degree Celsius. Okay, so think about when you cook with a pot. When you cook with a pot, the pots are usually made out of metal so that they can transfer that heat for you. Non-metals have higher specific heat capacity. So we have, upper end, it would take a lot more energy. Water has an unusually large specific heat capacity, which is good because it takes a lot of energy to heat up and cool down water, which is perfect because we know that we have lakes, rivers, oceans, we have it in our body. So if it wasn't high, so if it had a low specific heat, lakes, rivers, oceans, they would freeze when we had a cold day, which would be very bad for the wildlife and for the ocean and all the organisms living in it because they would all die every time it got cold. Okay, again, because your body is made out of 70% water, okay, your body temperature would change wildly with the weather. So it's good that water is a high specific heat. Okay, so again, your heat capacity is the amount of heat needed to raise the temperature of an object 1 degree Celsius. But your specific heat is going to take into account the mass. So that's going to be joules per grams times degrees Celsius. So specific heat includes the mass. Heat capacity does not take into account the mass. Doesn't matter if you have 1 gram, 5 grams, okay, but the specific heat does. All right, so again, so here is our equation. Okay, I wrote it on the first slide, but Q equals MCAT. Okay, so Q is going to stand for energy. We're either going to use joules or calories. Most of the time, we're going to be using joules. Okay, M stands for mass, which we're going to measure in grams. Specific heat. Okay, these are going to be given to you. Okay, the units are joules over grams times degrees Celsius. So our temperature needs to be in degrees Celsius, and delta T is the change in the temperature. So final minus initial. Okay, so again, Q is for energy. Remember, if it's positive, it's endothermic, negative, exothermic. Mass is how much something weighs, or the mass that it has. And then C is specific heat, and delta T is TF minus TI. So remember, delta means change. These are all your specific heat capacities that you need to know. Please notice that water in liquid, solid, and gas form is going to have a slightly different specific heat, so you need to make sure you pay attention to what state of matter water is in. So we're going to go through our first example. So it's asking us to determine the amount of energy. So we're now trying to find energy in joules. Okay, so we're trying to find joules required to raise a temperature of 7.0 grams of water. Okay, so it says water, so we know that this is H2O in liquid form. Okay, if it said ice, we'd know it'd be solid form, or water vapor, we know it'd be gas. Okay, and it's asking us to raise a temperature of 7.5 grams from 29 to 46 degrees Celsius. So we know here we're given a mass. So by reading it, the first number we run into is our mass, so 7.40 grams. Okay, we then know that we're given another set of numbers. We know that we're trying to raise it from 29 to 46. So that can help us to find our delta T. So we know we have the final temperature, and we know we have the initial. So we can just take the final, subtract it from the initial. So we can take delta TF, which is going to be 46.0 minus 29.0, and we can get our difference. So when we subtract that, we would get, and we got to look at sig fig, so 17.0 degrees Celsius is our change. It's a positive number because we're final minus initial, so we're raising the temperature. now we can go and find our specific heat, which we know is our C. So we look at our substance that we're talking about. We're talking about water in liquid form. All right, we'll go back to our chart. All right, we said water in liquid form, so here we go. Here is our specific heat. So we're going to plug in 4.184 joules over grams degrees Celsius. And then that means that our Q is our unknown. We're trying to find our energy. So we're going to just plug everything into our equation, which remember is Q equals MCAT. So Q, we don't know that. We know it's going to be found in joules, but that's all we know. Okay, we can then plug in Q equals M. We know our M. We know our C. And we know our delta T. We go through and we solve this. We calculate it out and we get a specific heat of 526 joules. Okay, we know it's joules because the grams will cancel out, degrees Celsius will cancel out, and we'll be left with joules, and that's our final answer. So we know that it would take 526 joules of energy to raise our 7.4 grams up into that temperature that we would need. Okay, so we'll try another example together. So we're going to try here. So it's asking how much thermal energy is absorbed. We have 750 grams. All right, so we know a mass. We know how much substance we're referring to. Okay, a water. So we know that we have water, H2O. We know it's in liquid form. So we know that we can go and find our specific heat. So we're going to go back. Okay, well, we just used the same exact one. It's still in water in liquid form, so 4.184 joules. All right, so we then are given two temperatures. All right, well, we know we can take our final and we can subtract that from our initial. So we can take 86.3 degrees Celsius, subtract it from 15.4 degrees Celsius. All right, and delta T then is going to come up to be 70.9 degrees Celsius. So now we have our change in temperature, which means, all right, we can find our Q. So we're going to plug everything in. So Q equals M. Notice sig figs. We have two sig figs here. C, 4.184. And T, 70.9. Okay, that's 3 sig figs, so our answer is going to have 2. So Q equals, when we calculate this out, you get a positive. But with sig figs, we would want to change this to equaling 220,000 joules so that we can get the right number of sig figs. So it would take us 220,000 joules of energy in order to raise this 750 grams of water by 70 degrees Celsius. So it would take a lot of energy to get us to raise it by that degree by our temperature. So I want you guys to try example 3 for homework. Please be careful about the sign of Q because you'll notice this time our temperature is decreasing. So think about what that would do with our Q. Please come in tomorrow with any questions on using our specific heat equation.